According to the National Electrical Code, you are not necessarily required to change the panel inside to a main lug panel when installing a meter socket with a disconnect. However, there are specific requirements that must be met to ensure code compliance and safety. Firstly, it is imperative to separate the grounds and neutrals throughout the entire electrical system. This separation must be maintained in the meter socket, the panel, and all other electrical equipment. The reason for this separation is to prevent neutral current from flowing through the grounding system, which can create a shock hazard. By keeping the grounds and neutrals separate, you ensure that any fault current will flow through the grounding system, tripping the overcurrent protection device and de-energizing the circuit. Secondly, the main disconnect in the meter socket must be properly rated. This means it should be rated for the maximum amperage of the service. The service amperage is determined by the size of the conductors coming into the building and the overall load calculation for the electrical system. The disconnect must be able to safely interrupt this amount of current in the event of a fault or overload. Thirdly, the panel inside must have backup overcurrent protection for the feeders connected to the meter socket. This backup protection can be provided by circuit breakers or fuses. The purpose of this backup protection is to ensure that if the main disconnect in the meter socket fails to trip, the overcurrent protection in the panel will still trip and energize the circuit. Having two main disconnects, one in the meter socket and one in the panel, is not a code violation in itself. However, proper coordination of the two disconnects is crucial. This means they must be designed to trip in the correct order to prevent damage to equipment or injury to personnel. Typically, the main disconnect in the meter socket should be sized to trip before the main disconnect in the panel. This ensures that the fault is cleared at the source, minimizing the amount of stress in the electrical system. When installing a new service, it is often necessary to obtain a permit from the local electrical inspector. This permit ensures that the installation meets all applicable codes and regulations. The electrical inspector will typically review the plans for the installation and inspect the work once it is completed. It is important to always follow the manufacturer's instructions for installing the meter socket with disconnect. The manufacturer's instructions provide detailed information on how to properly install the equipment and ensure that it functions safely and reliably. A qualified electrician should inspect the work to verify that it meets all code requirements. A qualified electrician has the training and experience necessary to ensure that the electrical installation is safe and code compliant. They can identify potential problems and make sure that the installation is done correctly. Let's delve deeper into the specifics of ground and neutral separation. In a properly wired electrical system, the neutral conductor carries the normal return current from the loads back to the source. The grounding conductor, on the other hand, is intended to provide a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip. When the grounds and neutrals are connected together, some of the neutral current can flow through the grounding system. This can create a voltage potential on the grounding system, which can be a shock hazard. It can also interfere with the operation of sensitive electronic equipment. To prevent this, the National Electrical Code requires that the grounds and neutrals be separated at the service entrance. This means that the neutral conductor must be isolated from the grounding conductor at the main panel. The neutral conductor should be connected to a neutral busbar that is insulated from the panel enclosure. The grounding conductor should be connected to a separate grounding busbar that is bonded to the panel enclosure and to the grounding electrode system. The grounding electrode system typically consists of one or more ground rods, ground plates, or metal water pipes that are buried in the earth. The purpose of the grounding electrode system is to provide a low impedance connection to the earth, which helps to stabilize the voltage of the electrical system and provide a path for fault current to flow back to the source. In addition to separating the grounds and neutrals at the service entrance, it is also important to separate them throughout the rest of the electrical system. This means that the grounds and neutrals should not be connected together in any of the branch circuits or at any of the electrical outlets or equipment. Each branch circuit should have its own dedicated neutral conductor and grounding conductor. The neutral conductor should be connected to the neutral terminal on the circuit breaker or fuse, and the grounding conductor should be connected to the grounding terminal on the circuit breaker or fuse. At each electrical outlet or piece of equipment, the neutral conductor should be connected to the neutral terminal, and the grounding conductor should be connected to the grounding terminal. The grounding terminal should be bonded to the metal enclosure of the outlet or equipment. Regarding the main disconnect rating, the National Electrical Code specifies that the main disconnect must be rated to interrupt the available fault current at the service entrance. Available fault current is the amount of current that would flow in the event of a short circuit. This is determined by the utility company based on the size of their transformer and the impedance of their distribution system. The available fault current can be very high, especially in commercial and industrial buildings. The main disconnect must be able to safely interrupt this amount of current without failing or causing damage to the electrical system. To determine the appropriate rating for the main disconnect, it is necessary to obtain the available fault current information from the utility company. This information is typically provided on a short circuit study. The main disconnect should be selected with an interrupting rating that is equal to or greater than the available fault current. The main disconnect must also be properly sized to carry the continuous load of the electrical system. The continuous load is the maximum amount of current that the electrical system is expected to draw on a continuous basis. The main disconnect should be sized to carry at least 125% of the continuous load. This is to allow for any future expansion of the electrical system. Overcurrent protection is a critical aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the electrical system from damage caused by overloads and short circuits. An overload occurs when the electrical system is drawing more current than it is designed to handle. This can be caused by too many appliances being plugged into the same circuit or by a malfunctioning appliance. A short circuit occurs when there is an unintended connection between two conductors. This can be caused by damaged insulation or by a loose connection. When an overload or short circuit occurs, the overcurrent protection device will trip, interrupting the flow of current and energizing the circuit. This prevents the wires from overheating and causing a fire. Circuit breakers are reusable overcurrent protection devices. They consist of a switch that is tripped by an overcurrent. When the circuit breaker trips, it can be reset by simply flipping the switch back to the on position. Fuses are one-time overcurrent protection devices. They consist of a strip of metal that melts when an overcurrent occurs. When the fuse blows, it must be replaced with a new fuse of the same rating. The choice between circuit breakers and fuses depends on the application. Circuit breakers are typically used in residential and commercial buildings, while fuses are often used in industrial applications. The National Electrical Code specifies the type and size of overcurrent protection devices that are required for different types of circuits. The overcurrent protection devices must be properly sized to protect the wires and equipment that they are connected to. Proper coordination of disconnects is essential for ensuring the safety and reliability of the electrical system. Coordination means that the overcurrent protection devices are designed to trip in a specific order to minimize the extent of the outage. In a coordinated system, the overcurrent protection device closest to the fault should trip first. This isolates the fault and prevents it from spreading to other parts of the electrical system. Coordination is typically achieved by using overcurrent protection devices with different time current characteristics. The time current characteristic is a graph that shows the amount of time it takes for an overcurrent protection device to trip at different levels of overcurrent. The overcurrent protection devices closest to the fault should have a faster time current characteristic than the overcurrent protection devices further away from the fault. This ensures that the overcurrent protection device closest to the fault will trip first, isolating the fault and minimizing the extent of the outage. If you're undertaking electrical work, understanding the National Electrical Code is crucial. The NEC provides comprehensive guidelines for safe electrical installations. Here's how it applies to your project. Firstly, NEC Section 250.24. It covers grounding of service-supplied alternating current systems. This section details the requirements for grounding the neutral conductor of the electrical service. It mandates that the neutral conductor be grounded at the service entrance to provide a lower impedance path for fault current. Secondly, NEC section 250.30 addresses grounding separately derived alternating current systems. If your installation involves a separately derived system, such as a generator or transformer, this section outlines the grounding requirements for that system. It specifies how to connect the grounding electrode conductor and the bonding jumpers to ensure proper grounding. Thirdly, NEC section 250.32 covers grounding requirements for outbuildings and detached structures. If the meter socket with disconnect is located in an outbuilding or detached structure, this section details the grounding requirements for that structure. It may require a separate grounding electrode system for the outbuilding. Fourthly, NEC section 230.70 pertains to the location of disconnecting mains. This section specifies where the service disconnect must be located. It generally requires that the service disconnect be readily accessible and located either inside or outside the building. Fifthly, NEC section 230.71 addresses the maximum number of disconnecting mains. This section limits the number of service disconnects that are permitted for a single service. It generally allows for up to 6 service disconnects, but there are exceptions to this rule. Sixthly, NEC section 230.82 lists the equipment permitted on the supply side of the service disconnect. This section specifies what types of equipment are allowed to be connected on the supply side of the service disconnect. It generally prohibits connecting any loads on the supply side of the service disconnect. Seventhly, NEC section 310.15 provides guidelines for ampacity of conductors. This section details how to determine the appropriate size of conductors for different applications. It takes into account factors such as the ambient temperature, the number of conductors in a raceway, and the type of insulation. Eighthly, NEC section 110.3. B covers examination, identification, installation, and use of equipment. This section requires that all electrical equipment be installed and used in accordance with its listing and labeling. It also requires that the equipment be properly identified and suitable for the intended use. Ninthly, NEC section 110.12 focuses on mechanical execution of work. This section requires that all electrical work be performed in a neat and workmanlike manner. It prohibits any sloppy or unprofessional work. Tenthly, NEC Article 408 pertains to switchboards and panel boards. This article covers the installation requirements for switchboards and panel boards, including the requirements for overcurrent protection, grounding, and conductor termination. 11thly, NEC Article 240 covers overcurrent protection. This article details the requirements for overcurrent protection devices such as circuit breakers and fuses. It specifies the types of overcurrent protection devices that are permitted for different applications and the requirements for sizing and coordinating the overcurrent protection devices. In addition to the NEC, your local jurisdiction may have its own electrical codes and regulations. It is important to check with your local building department to determine what codes and regulations apply to your project. Always consult the latest edition of the NEC and any applicable local codes. Electrical codes are subject to change, so it is important to stay up to date on the latest requirements.